Yeah. So the next periodic property we have is ionization enthalpy. So here I want you to understand the term enthalpy. Okay. So this is a thermodynamic term, students. So a little bit of the concept of enthalpy, I'll just brief you out. See, enthalpy refers to heat content of the system. Can you see it's given in this? Enthalpy refers to heat. Okay. Is it clear? It's a heat content of the system. And enthalpy is always denoted by delta H. That's a symbolic representation. Okay. And if you already you're aware of, are you aware of exothermic and endothermic process? Simple. What is exothermic process? If heat is evolved, you call it as exothermic. If heat is absorbed, you call it as endothermic. So this only is we call it as enthalpy. So symbolically we write it as delta H. If delta H is positive, it is endothermic. If delta H is negative, it is exothermic. This is alone, you remember. Okay. Sorry, it's exothermic. There's a mistake here. The spelling, it's exothermic. Got it? Keep this in mind. Because we will study the enthalpy factors, multiple. Have ionization enthalpy, electron gain enthalpy, all these are going to come into play. So enthalpy means what? It's a heat or energy. Energy is released. Its delta H will become negative. If energy is absorbed, delta H is shown as positive. This is something you have to understand. Okay. Now let's go to ionization enthalpy. Look at the word ionization enthalpy. What is it? It's an energy required to remove an electron from an isolated neutral gaseous atom. See what happens? Do you think an atom can lose electron easily? Can you remove electron easily from atom? See, I have sodium. Sodium is, you have neon 3s1. So can I remove the 3s electron easily from the outermost shell?
Yes, ma'am.
No, you cannot.
No, ma'am.
See, an atom is stable, right? Is an atom stable? See, compared to a molecule, atom is not stable. That's different thing. But is an atom stable than ion? Yes, no? So atom cannot lose electron on its own, cannot gain electron on its own. Are you getting it? So there is some energy changes involved. So see, when you take the electron in the outermost shell, isn't it the nucleus is showing its attraction over the valence electron? Isn't it? The electrostatic force of attraction will be there on the valence electron. So the atom cannot lose the electron on its own. Otherwise, no atoms will exist. Everything will become ions. Are you getting it? Is it clear? Atoms cannot exist. Everything will become ions. So losing ion or losing an electron is not that easy as you're thinking. There is energy that has to be invested. What is the energy? By giving energy, right? Energy has to be supplied to pull that electron out of the atom. Remember, this is the same thing you would have used in Einstein's photoelectric effect. Did you do Einstein's photoelectric effect? Yeah, what is the equation? E is equal to W plus KE, right? H nu is equal to H nu naught plus half mv square. What is this W?
Work function.
What is work function?
Minimum energy.
What does it do? Minimum energy?
Required to for the ejection of electrons.
Is it minimum energy required to remove the electron from the atom? Am I right? So are you not giving energy to take that electron from the atom? So what is your work function in other words? It is ionization enthalpy. Are you getting it? See, in your textbook, some questions will be there. It will be given sometimes as ionization enthalpy of sodium is so and so. That means the work function is that much. Are you getting it? Is that clear? There we call it as work function. Work function is nothing but ionization enthalpy. Is that clear? It's an energy required for the electron. Right. So to remove electron means what are you doing? See, this electron is held by the nucleus with the electrostatic force of attraction. So if you want to release this electron out of the bondage of nucleus, what should you do? You have to give that much energy to pull it out. Are you getting it? Whatever is the force of attraction between nucleus and this electron, that much energy is required to eject that electron out. That ejection of electron only we called as photoelectric effect. And that energy required to eject the electron is what? Work function. And here we are calling it as ionization enthalpy. Why am I calling it as ionization enthalpy? When you remove the electron from an atom, what will an atom become? Won't it become a cation? Removal of electron will lead to formation of cation. So you call this as ionization. And why the word enthalpy? It's an energy. Okay, that's a thermodynamic term. So it's an energy required to remove the electron from, so that's why it's removed to electron from the outermost shell. The most loosely held electron is being removed here. So a neutral gaseous atom is converted to what? A monopositive gaseous ion. Can you see that? So you call this as ionization enthalpy. Clear? Is that clear, students? What are the factors influencing ionization enthalpy? Effective nuclear charge. I told you yesterday. Effective nuclear charge will come everywhere now. So be thorough, understand that concept of effective nuclear charge. What is effective nuclear charge? Simple. It's a nuclear pull over valence electron. Okay. So what happens to ionization enthalpy with effective nuclear charge? See, when the nuclear pull over the electron is more, will the electron be lost easily? See, for example, an atom is having 2 shells and another atom is having 4 shells. So where is Z effective more? An atom with 2 shells or atom with 4 shells?
Atom with 2 shells.
Yeah. Isn't it? So here Z effective is more. So isn't it the valence electron is close to the nucleus? So can you remove electron easily from it? No, because the attraction of the positive charge of nucleus over the electron is more. So Z effective is greater. The outer electron is being pulled more force. So you have to invest more energy to take it out. Are you getting it? Is that clear? Right? So ionization enthalpy is directly related to Z effective. Means what? Greater the nuclear pull, more is the ionization enthalpy. Means more nuclear pull, it's difficult to remove the electron. Understand the verbal meaning of this. The more tightly the electron is held to the nucleus, okay, it is difficult to remove. So more energy is required. Okay. And in today's class, someone is asking a question. Oh, okay. Yeah. Atomic size. What is the relation between atomic size and Z effective? I told you yesterday. Inversely related. Yes. So if ionization enthalpy is directly related to Z effective, how was it related to atomic size? Inverse. So it's obvious now. See, 2 shells are there and the other one 4 shells. which atom is bigger? The one with 4 shells or 2 shells?
4
4
shells.
shells, isn't it? So, in which case removing electron is easier? The one with 4 shells. So, ionization enthalpy is inversely related to atomic size, means smaller the size of the atom, ionization enthalpy is greater. It is difficult to remove the electron, so more energy is spent. Can you get that? Are you able to get this relation? Next, shielding effect. Can you see all these are interrelated? Yesterday we told about the shielding effect and Z effective also. What is it? It's again inversely related. More shielding. Where is more shielding? In 4 shell or 2 shells? In which case you see more shielding?
Portion.
In 4 shells. Because there are more shells in between. So shielding is greater. The electron can be easily removed. Shielding is greater. Isn't it? So, are you able to relate? Friction power of orbitals. Did we discuss this yesterday? What did we say? S is greater than P, greater than D, greater than F. No? Right? Are you able to get it? So, means, what did I say about the penetration power? That effective order is this way. That's what you mean by penetration power. Which one is experiencing more nuclear pull? Which one is experiencing more nuclear pull?
S option.
Yes. So, is it easy to remove S electron? Okay, a simple logic I'll tell you. See, you have a configuration of aluminium. Aluminium is neon 3s2 3p1. Okay. Suppose I want to remove an electron from aluminium. I want to remove an electron. Which electron will it lose? 3p electron or 3s electron?
3p.
3p electron.
Yeah. Why? Because S is more penetrating. So P can be easily lost. Understood now? Are you able to apply whatever we did yesterday?
Ma'am,
Because
can you
S is...
explain this again, ma'am?
Yeah, 1 second. I'll take up aluminium. Fine. What is the electronic configuration of aluminium? 3s2, 3p1. Am I right? Yeah. Now, what is the penetration power of orbitals? S is greater than P, greater than D, greater than F. What do you mean by this? The Z effective is more for S. So, relatively, so if I put it like this, ease of removal of electron. I'll write like this. What is the order of ease of removal of electron? Which electron is easily removed? It's a reverse order. F is greater than D, greater than P, greater than S. Am I right? Are you able to understand? Z effective order is SPDF, right? In decreasing. Then ease of removal will be what? F electron is more easily removed than D electron, than P electron, than S electron. Did you get this relation now? Is that clear to everyone? Now you tell me, I have to remove an electron from aluminium. It is forming Al+. Which electron is lost? Will the 3s be given away or 3p? Both are from same shell, no? So which one is relatively experiencing less nuclear pull?
3p.
3p will.
Exactly. So which electron is lost? 3p is lost, not 3s. So if I ask you the configuration of Al+, what do you think will be the configuration of Al+? It is argon, it's neon 3s2. Understood? Aluminium is 3s2, 3p1. After losing one electron, it will be neon 3s2. This is something that you have to understand. Is that clear to everyone? So on what basis I'm able to work out this way? Penetration power. Clear? Lastly, we have stable configurations. Okay? Stable configuration means half filled and completely filled configurations are more stable. Okay? Half filled and completely filled you know that. So when an atom with half filled and completely filled is available, will it lose electron easily? No, it will not. No. So it will resist to lose. So you have to spend more energy to remove the electron in such cases. Is that clear? Got it? Clear? So what are the 5 factors? Tell me quickly. What are the 5 factors? Quickly. What is the first one? Ionization enthalpy is directly related to Z effective. More Z effective, more ionization enthalpy. Then atomic size is more, ionization enthalpy is low. Shielding effect is more, ionization enthalpy is low. More penetration power, ionization enthalpy is high. Means orbital with more penetration power cannot lose electron easily. Lastly, stable configurations, half filled and completely filled configurations will be more stable, so electron cannot be lost as easily as it seems to be. Okay, just a minute. I'll just switch on the fan students. Yeah, here. Now, successive ionization enthalpies. So what I mean by successive is one after the other. Like, see, removal of first electron, removal of second electron, removal of third electron. Okay. So you call this as successive ionization enthalpy. Some places, no, they give it as ionization energy, some they give it as ionization potential. All mean one and the same. Okay? They're alternate names given to this enthalpy. Okay. So what is the first ionization enthalpy? First ionization enthalpy, strictly no. Thermodynamically, we give it as delta Hi. It's called as ionization enthalpy. Okay. Now, for our understanding, I'll call this as IE1. Right? For our understanding, I'll call it as IE1. IE1 is the first ionization enthalpy. What is the first ionization enthalpy is doing? It's a formation of unipositive ion from a neutral atom. Please remember the equation. M gaseous is forming M plus gaseous. So there is a unipositive gaseous ion formed from an isolated neutral gaseous atom. Okay. That's the first ionization enthalpy. Second ionization enthalpy. From monopositive gaseous, you're forming dipositive. Okay. M plus to M2 plus. Dipositive. M2 plus to M3 plus. Okay. See, as simple as, so you have sodium is there. Sodium will form Na plus. If there is only one electron that sodium can lose to get the stability. You are aware of this. Now, when it comes to magnesium, how do you show magnesium? Mg forms Mg2 plus 2 electrons, you will see. It's not a one-step process. That's something that you have to remember. What are the steps involved? Magnesium first is losing one electron, and then the electron is lost. Are you getting it? So what is the overall reaction if I add? Is it not Mg giving Mg2 plus 2 electrons? So when Mg to Mg2 plus is taking place, how many ionization enthalpies are involved? 2, first and second. When aluminium is converted to Al3 plus, how many ionization enthalpies are involved?
3.
3, first, second, third. Get that. Okay. Is it clear? The total energy required to remove 3 electrons will be sum of all these ionization enthalpies. Ionization enthalpy 1 plus 2 plus 3. Is it clear? So total this much energy is required ultimately for the formation of Al3 plus from aluminium. Is that clear to everyone? Okay. So these are called successive ionization enthalpies. And the order of successive ionization enthalpies is the third ionization enthalpy is greater than, can you see? This is what is demonstrated for aluminium. Look at the energy. See, look at the values. I told you delta H is representing what? Energy. Symbolically, we are showing it as delta H. And what is the value here? If I don't write anything, it means everything is positive. Are you getting it? The positive value shows energy is absorbed. Okay? So in which case more energy is absorbed? Tell me. First, second, or third? Look at the values.
Third.
Third. Right? That means what's actually happening in the third case? Removal of third electron is more difficult, no? See, you are spending so much energy to remove the third electron means it's difficult to remove that electron. You are spending only 577 kilojoules to remove one electron, right? Then 1816 for removal of second electron. 2744 for removal of third electron. So the removal of third electron is more difficult than removal of second electron, than removal of first electron. Are you able to understand? So much of hidden meaning is there in just these values. We write symbols with values, but what is it actually giving you the meaning? Removal of third electron is difficult. So delta H I 3 is greater than 2, greater than 1. Means the third ionization enthalpy is always greater than second and first. Okay? Is it clear? Got it? Then variation of ionization enthalpy across a period down the group. Now you tell me. Yesterday I told you to keep that first Z effective. I told you to keep this chart ready. How is Z effective varying across a period down the group? Across a period, Z effective
Increases.
increases. Down the group, decreases.
Decreases.
And how was atomic size varying with Z effective? Inversely, no? So when it's inversely related to Z effective, how is it varying? It will be inverse. Across a period, atomic size decreases. Down the group, atomic size increases. Now, how is our ionization enthalpy related? Tell me now. What did we say?
Directly proportional to
Yeah.
Z effective.
Now, what do you think will the trend be?
Same as that of Z
Same
effective.
as Z effective. Can you see now? That's why I told you, keep this as a basis. Your Z effective is going to drive you throughout. It's a very, very, very important factor. Clear? So ionization enthalpy will decrease moving from top to bottom and increase moving from left to right. Clear? Understood? So, right, take a sheet and start, updating this time to time. Start with Z effective, atomic size, ionization enthalpy. The next property I am going to take up is what? Electron gain enthalpy. Look at the word electron gain. Means enthalpy associated during gaining of electron. As simple as that. So what will happen when electron is gained? A neutral atom will convert to anion.
Anion.
Negative charge is formed. What is happening in ionization enthalpy? Cation is being formed. What is happening when we are discussing in electron gain enthalpy? A negative ion is formed. Is it clear? So you call this electron gain enthalpy and symbolically we write it as delta Heg. Okay. Know the symbols. Clear? So addition of electron to a neutral atom can be positive or negative. Means energy can be lost or energy can be gained. It can be endothermic or exothermic, both. Is that clear? So which case it is endothermic? When it's endothermic, the values will be positive. So the positive electron gain enthalpy is only possible for inert gases, nowhere else. Only inert gases will have positive electron gain enthalpy. Is that clear? Noble gases have large positive electron gain enthalpies. Just remember this. Now, leaving inert gases, every other element, it will be negative. Okay? Is that clear? So, what happens is for all other elements, it will be negative. So, the question here, when I'm saying negative, it is less negative or more negative. That's only possible. Are you getting it? It can be less negative or more negative. See, what did we see in case of aluminium? The values are only positive, no? Delta H values. So what is a positive value tells? Energy is absorbed. More positive means more energy is absorbed. Less positive means less energy is absorbed. So here, in case of electron gain enthalpy, the values will be, by and large, will encounter only negative values. Only inert gases will have positive, rest all negative. So the values can be more negative or less negative. So what do you mean by more negative and less negative here? Okay. See, for example, I'll take you through your textbook. Once again. Can you see the students? Can you see this table? I want you to observe. What do you see for zero group? All positive, no? Okay. Don't try to remember every value. Just observe the pattern. Now, what do you see from hydrogen, lithium, sodium, fluorine, chlorine? Everywhere it's negative. Am I right? So what did I say? It's more negative or less negative? So what do you mean by more negative? What do you mean by less negative? See, delta H is minus 60 and I'm saying delta H is minus 328. Let me just observe this pattern. Okay. What exactly is it what information do I get? That means 60 kilojoules of heat is released. Whereas here, 328 kilojoules of heat is released. That's what is the meaning when I'm saying it's minus 328 and minus 60. Are you getting it? When I put it as plus, that much heat is absorbed. When I put it minus, this much heat is released. That negative sign is for release of heat. Clear? So, more heat is released, more energy released is an indication that gaining of electron is easy. Understand this. That's the key point. More heat released. So gaining of electron is easy. Less heat released, gaining electron is difficult. Did you get the meaning? This is something that you have to catch. So when I go from lithium to fluorine, gaining electron is easy or difficult? See, 60 minus 141 minus 328. What is happening? The value is becoming largely negative, no? It's becoming more and more negative. So more negative means more heat is released. Gaining electron is easier. So what happens to this addition of electron when you go from left to right? It becomes easier. Are you getting it? Addition of electron becomes easier when you go from left to right. Is it clear? Why? So here again comes delta HEG is again directly proportional to Z effective. Okay. It's directly proportional to Z effective. See, more nuclear pull. See, nuclear pull is greater. So when the pull of the electron, the influence of positive charge is more, will it attract electron or it will repel electron? It will attract, no? If the power of positive charge in the centralized nucleus is greater, it's exerting more force. So will it attract electron or will it let go the electron? That. So gaining electron is easier now. Understood? So more Z effective, more delta H. That's what is happening. When you move from left to right, Z effective increases. So what happens to electron gain enthalpy? So here, that's why we use the word negative electron gain enthalpy increases. Understood? We use the word negative electron gain enthalpy. That means gaining electron is easier. Clear? And down the group, it decreases. Clear? I'll give you the general trends now. I'll speak about the anomalies later. Let me tell the general trends to be aware of. Then special cases I'll explain you later. Exceptions. Okay. So the next periodic property we have is again successive electron gain enthalpies. Okay, electron gain enthalpy 1, electron gain enthalpy 2, electron gain enthalpy 3. Second electron gain enthalpy of oxygen is positive, whereas first electron gain enthalpy is negative. Look at the value. What does it mean? When first electron is added, energy is released. Okay. When the second electron is added, energy is absorbed. What do you understand from this? Addition of second electron is difficult. Addition of first electron is easy. Are you getting it? Addition of first electron is easy. Second electron is difficult. That's why energy is absorbed. Means to add electron, I have to give energy. See this? Are you getting the verbal meaning? First electron, it's losing on its own, energy is given up. It's an easy process. But to add the second electron, you are spending energy to, insert the second electron into the atomic core. It's becoming difficult. So when it comes to successive ionization, successive electron gain enthalpies, here the value will become lesser. Why? Observe this carefully. Electron, first case, it's added to the atom. Now, what is happening when it's added to the atom? It is forming a O negative. In second case, what is happening? Already, isn't it, there is a negative charge on oxygen? O minus. So this electron and this negative charge, they too repel. So addition becomes difficult there. Are you getting it? Is it clear? Already, it's something like this. A negative charge is already like, it's acting like a shield. And the second electron has to overcome the repulsion to enter the atom to form O2 minus. Okay? So the O minus, should give a gate pass. Only then the second electron can enter. Isn't it? O minus is also negatively charged. Electron is also negatively charged. So there is a repulsion. Clear? Next. Again, I told you the factors influencing it. I told you same. Everything will be same. Except that, you can take it as mainly Z effective. More Z effective, more negative electron gain enthalpy. So the negative electron gain enthalpy, I'm writing it as minus delta HEG. Okay? It increases across a period, decreases down the. Okay? So which is the element with highest electron gain enthalpy? See, it is increasing across the period and it's decreasing down the group. So what do you expect? Noble gases are having 0. So you expect fluorine to have highest. But it's not that. The electron gain enthalpy of chlorine is greater than fluorine. Very, very, very important. Okay. Why? The reason is because of small size of fluorine atom, there is a repulsion between the non-bonding electrons. You know what are non-bonding electrons? Non-bonding electrons are lone pairs. See, fluorine is there. There are lone pairs. Okay? There are lone pairs of electrons on fluorine. So to add the electron, what happens is repulsions will be more. Due to small size, repulsions are even more higher in fluorine. That's why it's easy to add electron in chlorine compared to fluorine. Clear? The next property we have is electron. Now we will speed up. The next property we have is electronegativity. It's a tendency of a bonded atom to attract shared pair of electrons. Okay? See, you have hydrogen, chlorine. It forms HCl. With hydrogen is forming HH bond. So when both the atoms are of same size, relatively there is no difference. Electrons are equally shared. But in HCl, what happens? the shared pair of electrons is more inclined towards chlorine. The electrons are pulled by chlorine more. Why? Because the Z effective of chlorine is greater. Are you getting it? The Z effective of chlorine is greater. The shared pair of electrons is pulled more towards chlorine. So this tendency of a bonded atom attract shared pair of electrons is called as electronegativity. See, very simple. I have chlorine, I have sodium with chlorine, and then I have sodium with hydrogen, and hydrogen and chlorine. Observe this. H and Cl will form HCl. NaCl, you know, Na is positively charged, chlorine is negatively charged. How are the charges with sodium and hydrogen? A metal will always lose electrons. Always the metal will lose electron. So here also it's Na plus and H minus. Okay. See, when it comes to sodium, hydrogen is losing electron. But when hydrogen is with chlorine, what is happening? When it's with sodium, hydrogen is gaining electron. Whereas when hydrogen is with chlorine, hydrogen is giving the electron density to chlorine. So this is relative. Are you able to understand? We call it as a relative tendency. Element to element, the nature behavior changes. When hydrogen and sodium are bonding, hydrogen will gain electron from sodium. When hydrogen and chlorine is bonding, isn't it HCl and water will give what? Is it not forming H plus and Cl minus? You know this, right? So with Cl, what is hydrogen doing? It is losing electrons. It forms a proton. So this tendency of a bonded atom to attract electron is called as electronegativity. Okay? Is it clear? So electronegativity scale was designed by many people gave this. So one of the successful theories came up with from Pauling, and currently we are using Pauling scale. And the values, though you don't remember all the values, at least you remember that for these three elements. You will be applying this a lot. Okay? Fluorine is 4, oxygen is 3.5, nitrogen and chlorine are relatively same is 3.0. And this order you remember. This order you remember. F is greater than oxygen, greater than bromine. Clear? This order you remember. You know, if you don't remember other values is okay. At least the order, which is most electronegative and relatively which is least electronegative. Is that clear? Again, electronegativity. What did I tell you? Basically, it's a tendency of an atom to gain electron. It's as simple as that. It's tendency to gain electron. Okay? It's a tendency to gain electron. What happens to tendency to gain electron with respect to Z effective? Will it increase or decrease? More nuclear pull, electron is attracted or repelled. Sometime back I told you. When Z effective is more, what will happen to electronegative? Electronegativity will again increase with Z effective. Isn't it? See, more Z effective, more nuclear pull, it's attracted. Because nuclear pull is more. The nucleus is pulling the electron. So electron is attracted towards the nucleus. So more Z effective, more. So what happens across a period down the group? Same as Z effective. Are you able to see now? Are you adding to your chart? I told you to, time to time fill up this. Because every periodic property, I'm going to update this now here. Is that clear, students?
Excuse
So,
me,
which is
ma'am.
the most electronegative element? I've given the values. Which is the most electronegative element?
Fluorine.
Yes. It's not chlorine. But which is the element with highest electron gain enthalpy? Chlorine, not fluorine. This is something that you have to register. It's a very, very, very important distinction. Okay. Electron gain enthalpy of chlorine is more negative than fluorine. So chlorine is having more negative electron gain enthalpy. Whereas electronegativity is concerned, fluorine is more electronegative. Why? Because of small size, because of Mohs effective, all these factors come. Okay. Is that clear? Got it? So, what happens across a period down the group? Can you see? Same thing. Clear? So, now on it will be easy for you students. Because you understood electronegativity, the remaining properties will become more easy for you. The next property is opposite of electronegativity. What is it? Electropositivity. What is electronegativity? Tendency to gain electrons. Electropositivity will be tendency to lose. So what will that be? Isn't it opposite of electronegativity? So it's inversely related to Z effective now. So come on, I want you to fill up. Things are there on the screen. The element with highest electropositivity actually is francium. Since francium is radioactive, we'll take cesium here. Okay. Oh, 1 second, students. Next. Oh, can I share the screen once again? Just a minute. My system is hung. I'm not able to scroll the page. Just a minute. Children, what are you seeing?
The black screen.
Okay. 1 second. I stop sharing. 1 second. Are you able to see now? Is it visible, students?
Yes,
ma'am.
ma'am.
Yes, ma'am.
So maybe whatever I've written earlier got erased. So I hope you have updated it, all of you. Yeah. So put the list here. Then we have your Z effective. Then we saw atomic size. Then ionization enthalpy, negative electron gain enthalpy, electronegativity, electropositivity, isn't it? Across the period, down the group. Okay. So if you see, most of the properties are going the same way as Z effective, right? And how about electropositivity? It's inversely related to electronegativity. So tendency to gain electrons is more across a period. So tendency to lose electrons will be decreasing. And it will be opposite of electronegativity. Clear? Next is metallic character. Metallic is the tendency to lose electrons again. So what is metallic character a function of? What's the metallic character a function of? How will it behave? Behave as electronegativity or electropositivity?
Electropositivity.
Correct. So metallic character will, what will happen? Same as electropositivity. It will decrease across a period and increase down the group. If you see your periodic table, where is our periodic table? 1 second. What's happening? How is it appearing for you? Is it blur? Or you can see the screen? Some problem is there. Wait. See the metallic character, just see, your periodic table. If you have a periodic chart, observe it and see. You will observe, where you have sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine. Can you see now? What is happening across the period? It is metallic character is increasing. You see more of non-metals on the right. We told that in P block there are non-metals. And the remaining you see metals. So metallic character is decreasing across the period. Okay. And like particularly if I take this particular group 14, carbon, silicon, germanium, tin, lead. Just see this pattern. Observe this pattern. It's a clear transition you can see here. What are carbon and silicon? Right? What are they? Carbon is a non-metal. Then again, when it comes down, germanium is a metalloid. And tin and lead are metals. So isn't it a clear transition you see from non-metallic character to metallic character? Anything is not working, students? Any problem? Can you see the screen?
Yes, ma'am.
Yes,
Is
ma'am.
it visible? Yeah. So when you go from left to right, what is happening? You go from metal to non-metals. And top to bottom, from non-metal to metal. So metallic character increases down the group, decreases across a period. Yeah. And the opposite is non-metallic. So what is non-metallic character? It's a function of? It's a function of what? How does it vary? It varies with same, whatever I said now. Metallic is function of electropositivity, means non-metallic is a tendency to gain electrons. It's a function of electronegativity. So non-metallic character will increase across a period, decrease down the line. Got it? Is that understandable? See, the moment you understand electronegativity, there are few properties which are directly related to electronegativity and few are directly related to electropositivity. So electronegativity and electropositivity are opposite in nature, you see, isn't it? So metallic goes with electropositivity, non-metallic goes with electronegativity. Is that clear? Next is acidic and basic character. Can you name some acids? Not many, just one or two acids. Anybody?
Sodium, sir. Hydrochloric acid,
Formula?
HCl,
Okay, one more.
Sulfuric acid.
Formula?
H2SO4.
Right. Okay, done. That's enough. Not many. And can you give me examples of bases?
NaOH.
NaOH. One more.
NGOH.
MgOH twice. Valency is 2. Okay. So what is that you see common in NaOH and MgOH twice? Don't tell me OH. Don't tell me OH. That's a normal perception. I want you to observe another way. What's common in NaOH and MgOH twice?
both are metals.
They have metals. Correct. Both are not metals. So they are metal hydroxides. Can you identify that? And what do acids have? Now you must have got the answer. What do acids have? Do they have metals?
They have non-metals.
Yeah, they are formed by non-metals. So now tell me, acidic character is a function of non-metallic character. Non-metallic character is a function of electronegativity. Can you see the relation? Are you able to get the loop? And metal hydroxide, so basic character is a function of metallic character, which in turn depends on electropositivity. So how will my acidic character and basic character behave across a period down the group? You tell me. So acidic character will
increase across a period.
increase because it's same as electronegativity, right? Same as non-metallic character. So decrease down the group. And basic character, opposite. Can you see, students? You understand? Isn't it easy now? Because everything you're relating to what fundamentally? Which is that factor? The only factor which drives all these periodic properties? Which is that factor?
Z effect.
Exactly, Z effective. So all these periodic properties, that's why yesterday I was emphasizing so much. If you're thorough with one Z effective, you are thorough with periodic table chapter, periodic properties. Here. Next, the next character we have is oxidizing reducing power. How do you define oxidizing power? Oxidizing power is the ability of an element to undergo reduction. What do you mean by ability to undergo reduction? How effectively the substance can act as oxidizing agent. The substance can oxidize another substance. That is what is called as oxidizing power. So oxidizing power is not the ability to undergo oxidation. Many take it wrong way. Please don't take it that way. Ability of an element to undergo reduction. Please mark this. Not undergo oxidation. So it has an ability to undergo reduction. It can effectively act as oxidizing agent. Okay. What is oxidation? What is reduction? Reduction is gaining of electrons. Are you getting it? Reduction is gaining of electrons. So oxidizing power depends on what? Tendency to gain electron. In other words, again, electronegativity. So oxidizing power is the ability to gain electron. Clear? Is that understandable? And what is reducing power? The opposite of it. Ability to act as reducing agent. So it's ability to undergo oxidation now. So it has a tendency to lose electrons. So reducing power is a function of electropositivity. Now all these are interrelated. Electronegativity, electropositivity. Metallic. So electronegativity is related to what? Now it's related to non-metallic character. It's related to acidic property. It's related to oxidizing power. Can you see now? And electropositivity, opposite. Metallic, basic, and reducing. Clear? That's why metals are very good reducing agents. Non-metals are powerful oxidizing agents. Are you getting this now? Yeah? Clear? So that's about the periodic properties fundamentally. Clear now? This chart is something that I want you to do this, stick it somewhere. Just like we say, no, periodic table is important. If you have this chart, you have it, you file it. Believe me, this is going to be a very, very, very good resource. Anytime you want, you refer to this chart. You will know the periodic trend. How do elements behave across a period down the group? Which property is increasing? Which property is decreasing? Thoroughly from this chart. Okay? Is that clear, students? And any doubts so far? Anybody? Okay? Yeah, anyone is having a doubt, children? If so, you can go
Excuse me,
ahead.
ma'am.
Yeah, tell me.
Ma'am, I have a doubt. How is electronegativity directly proportional to Z effective?
Okay. What is electronegativity? Tendency to gain electron. Isn't it? Now, if the nuclear